Hi, everybody. So in today's session, we are going to discuss about the various applications of crystal field theory or crystal field stabilization energy. And the first application that we are going to discuss is about spinels. Okay, spinels. So please write down the heading, spinels. We'll be covering this in probably 2 videos. First one would be spinels. Okay. What are spinels? Spinels are those compounds who have got a general formula of A, B, 2O4. Okay. Understand that A and B can be equal. A and B may not be equal. What are A and B? A and B are the metal sites. Okay, A and B are the metal sites where A generally is in +2 oxidation state, which is a second group metal or a transition metal. Or a transition metal. And B, how many B's are there? There are 2 B's, which would be in +3 oxidation state, belonging to the third group, or it can be any transition metal. This is how it is, generally. Understand that any systems that you have, so this A and B can be same, it may not be the same. For example, let me take this example. Let's say you take Mn3O4. So Mn3O4. So you have one Mn in +2 and you have 2 Mn species in +3. This is a case where both A and B sites are the same. You can have cases where they are not the same as well. For example, let's say you took MgAl2O4, even that is possible, where Mg is in +2 and there are 2 aluminium +3 ions. So they may be the same, they may not be the same. Now you will be learning about the octahedral, tetrahedral sites, voids in solid state. But for your information, please note it down that if a species, if any compound has n octahedral sites, number of octahedral sites, let's say, is n, then number of tetrahedral sites would be 2n. Oh, sorry, it's the other way. It's the other way. If this is n, the other one would be 2n. Okay. So the number of octahedral sites is equal to 2 times the number of tetrahedral sites. That's why you can, okay, we'll get to know that. Okay, so this is the very basic formula of how a spinel look like. So a spinel has Ab2O4 as its formula, where A is in +2 oxidation state and B is in +3 oxidation state. Now, based on their positions of octahedral and tetrahedral sites that they occupy, they are mainly divided into 2 types. Ab2O4 is divided into 2 types. One is where the +2, the metal which is in +2 oxidation state, takes up the tetrahedral site, and the 2 B atoms which are in +3 oxidation state takes up the octahedral site O4. Okay, so A +2, which is 1 in number, takes up the tetrahedral site. 2B +3 takes up the octahedral site. So you can see number of octahedral sites is equal to 2 times the number of tetrahedral sites. If this is the case, the spinel, the type of the spinel is called a normal spinel. This is called a normal spinel. So the application that we are trying to learn is to predict the site selection of the spinel. If some spinel is given to you, you have to predict the site, whether A +2 will occupy the tetrahedral site or octahedral site is what you try and find out through CFSE. And the other case is where A +2 takes up the or I'll write it the other way. It is where the tetrahedral site is occupied by tetrahedral site. And in the octahedral site, you will have one 2 plus cation and the other 3 plus cation, O4. Okay, so you had one A plus 2, which would occupy the octahedral site, and you have got two B plus 3, out of which one will occupy the tetrahedral site and the other one would occupy the octahedral site. So if this is the case, such a spinel is called inverse spinel. Inverse spinel. So here also you can see one tetrahedral void and you have two octahedral voids. Always number of octahedral voids is equal to 2 times the tetrahedral voids. That is clear. So you have to understand the basic formula of a normal spinel and an inverse spinel. So in normal spinel, plus 2 will take up the tetrahedral void, and in inverse, plus 3 will take up the tetrahedral void, and the rest will go to octahedral. So we have to try and predict whatever spinel is given to you, whether it is normal or whether it is inverse, is what we are going to try and find out. So let's try. Let's do one by one. The first question is MN3O4. You have to find whether this is a normal spinel or whether this is an inverse spinel. So for that, you have to first of all identify the metals that do exist in +2 and +3 oxidation states. Here A and B sites are the same. So you have Mn+2 and you have Mn+3. Okay. So all that you have to do is, I'll show one example and the remaining examples you can do it on your own. Mn+2 has a configuration of D5 and Mn+3 has got a configuration of D4. You fill both of these configurations under tetrahedral splitting. Oh my God, no. So sorry. You fill these configurations under octahedral splitting. What is octahedral splitting? You have T2G at the bottom. You have EG at the top. Who is the ligand? Oxide, O-2 is the ligand, and we know oxide is a weak field ligand. So if you have to fill 5 electrons over here, 1, 2, 3, 4, 5. This would be the configuration, T2G3EG2. You calculate the CFSE, exactly half filled, so your CFSE will be 0. Okay. Similarly, you fill Mn+3 for octahedral positions as well. So T2G, EG is what you have. 4 electrons to fill. 1, 2, 3. Fourth one will easily jump because you have a weak field ligand. The splitting will be low and the fourth one can jump. As a result of which you get a CFSE. Correct? So you have 3 electrons in T2G giving you -1.2 delta O, and you have 1 in EG which is +0.6. So a total of -0.6 delta O. So what do you understand from this? From this we understand that I already told you in the previous sessions that minus denotes stabilization. So when you put Mn+2 in octahedral geometry, your CFSE is 0. But when you put Mn+3 in octahedral geometry, it is -0.6 delta O, meaning it is more stabilized. Minus meaning stabilized. So you have to put Mn+3 in octahedral geometry so as to attain stability. Okay, so you can note it down. CFSE of Mn+3 is higher than Mn+2. Therefore, Mn+3 prefers octahedral sites. Why? Because higher the value, we already know that the splitting or the splitting of octahedral is higher than that of tetrahedral. This too we already know. From factors affecting CFSE, splitting energy, we have already learned all these stuffs. So if you put Mn plus 2 in octahedral, your stabilization energy is 0. And if you put Mn plus 3 in octahedral geometry, your stabilization is minus 0.6. So it says that Mn plus 3 is what prefers octahedral sites over Mn plus 2. Okay, so how would we write the formula? Mn plus 2 we have, and we have 2 Mn plus 3. We already said that Mn plus 3 prefers octahedral site. So the other one would automatically go to the tetrahedral site, and we have ligand O4. What is this equal to? A plus 2 tetrahedral, 2B plus 3 octahedral O4, and this gives us a normal spinel. Normal spinel. So this is how you do it. Okay, let's try a few more. Let's say you have Fe3O4. Fe3O4. Okay. So we have Fe in plus 2 and we have Fe in plus 3. Fe plus 2 is D6. Fe plus 3 is D5. Again, we have the ligand is oxide, which is a weak field ligand. So T2G EG gap will be small. You have to fill 6 electrons. 1, 2, 3. Fourth one will easily jump, and then sixth one will pair. So you have T2G4 EG2. Your CFSE value after you calculate for octahedral geometry is going to be minus 0.4 delta O. Over here, again, T2GEG, gap will be small because the ligand is weak. 1, 2, 3, fourth one can easily jump. Exactly half filled, CFSE is going to be 0. Configuration is T2G3EG2. So you can understand that here you have to put Fe plus 2 in the octahedral site to gain stability. Because if you put Fe plus 3, your CFSE is 0. No stability. Here, you have got a minus 0.4 units of stability for Fe plus 2. That means Fe plus 2 will go to octahedral geometry. Okay. You have 2 octahedral sites. Understand, you have 2 octahedral sites. So there is one tetrahedral site and there are 2 octahedral sites. So one of the octahedral site is taken up by Fe plus 2. Correct? And we already know that in any spinel you have one Fe plus 2 and you will have the other 2 as plus 3. So this is how you will distribute. So plus 2 will go to octahedral, plus 3, one of it will go to tetrahedral, one more plus 3 is there, which will go to octahedral, O4. This is how it should be. Correct? So Fe plus 3 is taking up the tetrahedral position. Fe plus 2 and plus 3 are taking up the octahedral position. And this corresponds to an inverse spinel. This is how we do it. Try the next one. Will come only through practice. Ni3O4. Or let's do something else. We'll do mixed spines. Mixed means not the same ones. NiCr2O4. NiCr2O4. So the first one, which is just 1 in number, stoichiometry, that is going to be plus 2. And the other one is going to be plus 3. Right? Now, nickel plus 2, D8 configuration, chromium plus 3, scandium, titanium, vanadium, chromium, D3, correct? Chromium is 4s2, 3d4. You have to lose 3 electrons, so it is going to be the D3. Okay. This is how it is. So let's start filling T2G, EG, T2G, EG. So here you have to fill 1, 2, 3, 4, 5, 6, 7, 8. So if you calculate your CFSE, that is going to be minus 1.2 delta O. Here you have just 1, 2, 3, whose CFSE is also going to be minus 1.2 delta O. Now you have come to a point where the CFSEs are the same for both. Okay, the CFSEs are same for both. So what we can say over here is understand that here this one is in +2 and the other one is in +3. Correct? So as your oxidation state increases, we have learned that your splitting increases. The splitting of +3 will be greater than +2. So this value of +3 will be higher than this value of a metal which is in +2. So the CFSE of chromium 3 plus is high. So if the chromium 3 plus is more stabilized, if that is more stabilized, there are 2 chromium 3 plus species which will go to octahedral site because that is more stabilized. The other one, nickel +2, will take up the tetrahedral position, and this corresponds to a normal spinel. This corresponds to a normal spinel. Okay? Let's do one more question. FeCr2O4. So Fe +2, Cr +3, Fe +2 D6 configuration, Cr +3 D3 configuration. Here T2G, Eg, here also T2G, Eg. So 1, 2, 3, 4, 5, 6. So your CFSE value after calculation will be minus 0.4 delta. Right. Over here it is 1, 2, 3, which is CFSE value over here is going to be minus 1.2 delta O. See, here it is stabilized by only 0.4 units. Negative sign notates stabilization. Fe +2 in octahedral site is stabilized by only 0.4 units, but Cr +3 is stabilized by 1.2 units. So Cr +3, 2 in number, will go to the octahedral site. Iron +2 will take up the tetrahedral site, O4. Again, this is a case of normal spinel. Right? This is a case of normal spinel. Last example, CO3O4. So you have cobaltin +2, cobaltin +3. Cobaltin +2 is D7. Cobaltin +3 is D6. So T2G, EG, you have to fill 7 electrons. 1, 2, 3, 4, 5, 6, 7. So your configuration is T2G5, EG2. Your CFSE would be minus 0.8 delta O. Over here, T2GEG, but remember, I have always told you, whenever you have cobalt +3, you have to be careful. With cobalt +3, oxide acts like a strong field ligand. There are only 6 ligands which acts weak with cobalt 3+, rest everybody is strong. So oxide is strong over here. 1, 2, 3, 4 cannot jump. This will pair up over here. Got it? This will pair up over here. So as a result, the CFSE over here is minus 2.4 delta O. So cobalt +3 is stabilized by 2.4 units, while +2 is stabilized by only 0.8 units. So cobalt +3, 2 in number, will go to the octahedral site. Cobalt +2 will take up the tetrahedral site, O4, and hence this is a normal spine. Okay. So in most of the cases, you can use this method to actually find whether it is normal or whether it is inverse. But in the question papers, you get tricky questions wherein, for example, let me tell you, example, NICR 2 times O4, this particular example. Okay, this particular example. We have already done this example. Okay, we have, oh, not this one, sorry, NIAL2. NIAL2. Okay, this particular example. In this particular example, we might do some calculation and we might find whether it is inverse or normal, but actually this is a mixed spinal. Mixed spinal means a small fraction of the spinal will remain normal and the other small fraction will remain inverse. So what I would suggest is I have taken a table from Hughie, and wherein they describe some parameter called lambda. Values of lambda of spinals. Okay? So wherein A is in +2 oxidation state, B is in +3 O4. So this table, I would request you to by heart it so that you don't end up getting negative marks. Write it 2 to 3 times and then it will come with a flow. Okay. So over here we have, along the first row, please note it down. We have Mg 2 plus, manganese, iron, cobalt, nickel, copper, zinc. Okay, these are the A metals that they are talking about. And the B metals, I'll write with a different color. Aluminium +3, chromium, iron, manganese, and then cobalt. Okay. These are the metals in +3 that is given in the table. Now I'm going to tell you some values. 0, 0, 0.45, 0, 0.1 and 0. No value, no value, no value. 0, 0.5, 0, 0.5 and 0. Under nickel, 0.38, 0, 0.5, no values. No value, 0, 0.5, none. And then you have got, this is the table. Please pause the video, check the values. Let me check the values as well. 2, 5, 1, 5. Okay. So if lambda is equal to 0, then your spinal is normal. If lambda is equal to 0.5, then your spinal is inverse. If your lambda is greater than 0 and less than 0.5, then it is mixed spinal. This is the summary of the table. Okay. Now, any complex that is given to you. Now, once there was a question which was asked, which said, along with Fe+3, which of the following metal ions would give a normal spinal? And some options were given along with Fe+3. So if you check, This is 0.45 mixed, 0.1 mixed, 0.5, 0.5, 0.5, 0.5, all of them corresponds to inverse spinel. So Fe plus 3 gives a normal spinel with zinc 2 plus. And the correct answer was zinc 2 plus. You can answer that only if you know this table. Because there are certain experimental observations which you cannot predict it using the equation that we did. We can do some of them, but not all of them. So what I would suggest is to learn this table. Some way or the other, please learn this table. Okay, you learn the order of the plus 2 cations, you learn the order of the plus 3 cations. And you learn this table. Okay, so from this table, it is clear that magnesium and aluminium, if you have, for example, this was asked in the question, Mg2Al3O4. This is a PYQ. What kind of spinel is this? If you know this table, it is a normal spinel. Okay. Similarly, the question that I said, Fe plus 3 forms a normal spinel with which of the cation? It is with zinc plus 2 only. Now, the next one, aluminium forms mixed spinel with which cation? So you have to know that it is with Ni2 plus only. Rest, everything is normal. Okay, so only and only if you know this table, you can write such tricky questions. Otherwise, you will end up getting negative marks. MgAl2O4, okay? I think I wrote something else over here. It's Mg in plus 2, Al in plus 3, 2 times O4. This question was asked, normal spine. So please, 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 very important, very, very important, this values of lambda. This is a parameter which is experimentally found and this is there in Huey. Okay. Yeah, so I think we'll end the session. And in the next session, we'll discuss about the remaining applications. So this table is important. Please learn that. Okay. All right. Thank you.